This lesson is about finding infinite limits. So infinite limits, that means that the graph either goes up and up and up forever, which is positive infinity, or down and down and down forever, which is negative infinity. So in this lesson, we're going to be determining infinite limits from the left and the right, and find and sketch the vertical asymptotes of the graph of a function. Okay, so I'm going to turn out the lights so we can see the board better, and I'm going to graph the first function for you. Okay, so I'm going to use Desmos to graph this function on your notes. So it says let f be the function given by f of x equals 3 divided by x minus 2. I'm going to type that in this box here. Y equals 3 divided by x minus 2. Okay. And as you can see, it might be a little too white, so I'm going to draw on it to show you better. Okay, so as you can see, we've got something like this. And something like this. Okay. So this is our graph, and it says we want to find the limit of this function as x approaches 2. Well, if you notice, when x approaches 2, we've got from the left, it's going down like this. And from the right, it's going up like this. And I drew in right there a vertical dotted line, which is called an asymptote, which I'm going to explain more later. But it says, let's examine this the way we did it before at the beginning of this chapter. So I'm going to create a table of points now that goes with your notes. Okay, so I'm going to type these x's that are on your notes into my table, and we will get the numbers you need to write in your boxes. Okay. Okay, so I have typed the numbers in my table, and I'm going to tell you what they are since I know it's hard for you to see it. Okay, so first, when I typed in 1.5, I got -6. For 1.9, I typed that in and I got -30. When I typed in 1.999, just 2 nines actually, sorry, got a little crazy with the nines. I got -300. Okay, then I typed in 1.999, so we're getting closer and closer to 2, and I got -3,000. So I want to point this out. If you can notice, these are getting more and more negative. Like they're getting larger and larger, but more negative. And you can see that in this picture because it is sharply going down, more and more negative as we get closer and closer to x equals 2. Okay, so now we're going to talk about what happens from the right side. So when I typed in 2.0001, I got 30,000. As I typed in 2.001, I got 3,000. As I typed in 2.01, I got 300. And 2.5, I got 6. Okay, so this is further from 2. This is getting closer to 2. So as I come in from the right and go closer to x equals 2, it's getting bigger and bigger and bigger. So that's going towards positive infinity, as you can see from this picture. It's getting more and more positive. It's going more and more up, like that. So from the left, we have it's getting more and more negative. From the right, it's getting more and more positive. So below the table, it says, what is the limit approaching from the left? Well, these numbers were from the left. And from the left, it's approaching negative infinity. When it says, what is the limit as x approaches 2 from the left, you're going to say that that equals negative infinity. Okay, so that equals negative infinity, and I'll space that out a little bit so it's more obvious. Okay, so it equals negative infinity. All right, so then it says, what is the limit approaching from the right? So here, these are numbers from the right. This is further from 2. This is getting closer to 2. So as we get closer and closer to 2, our limit was positive infinity. So we're going to write the limit as x approaches 2 from the right is infinity. Okay. And like I said before, you can see that from the picture because this, we're coming in from the left, and it's going more and more down, more and more negative. Here we're coming in from the right, and it's going more and more up, more and more positive. So that's going towards positive infinity. Okay, so that's the first part. Now I'm going to read some more to you. It says a limit in which f of x increases or decreases without bound as x approaches a number c is called an infinite limit. Okay. Be sure that you see the equal sign in the statement the limit f of x equals infinity does not mean that the limit exists. On the contrary, it tells you that the limit fails to exist because this is unbounded. It just keeps going down, 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 down. This one just keeps going up, up, up. It doesn't have a concrete place where it stops. It goes on forever. Okay. So now we're going to look at example 1. And we're going to talk about determining infinite limits from a graph. Kind of talked about here, but we're going to explore it some more. Okay. So I'm going to erase this and talk about this picture. So stand by. Okay, so I'm going to draw you the picture under example 1 now. So it looks like this. Okay, so we have x is 1 right there, x is 2 right here, and x is 0. And it looks like we have this dotted line, x equals 1. So I'm going to draw that in. This. And then our graph itself is going to have this sort of behavior. Let's make it red. So it comes in like this and this. Okay, so something like that. Okay, so it says on your notes here, if it were possible to extend the graph in this figure toward positive infinity, you would see that the graph becomes arbitrarily close to the vertical line x equals 1. So it's going to get closer and closer to this line x equals 1, but it's never going to touch it. And because it never touches it, that's what makes it an asymptote. So definition, if f of x approaches infinity or negative infinity, as x approaches c, so in this case, as x approaches 1, from the right or the left, then the line x equals c, or x equals 1 in this case, is a vertical asymptote of the graph. Okay, so if it approaches some sort of vertical line and never touches it, that vertical line is the asymptote. Okay. All right, so now I'm going to show you how to find if a function has a vertical asymptote just from the equation. We're going to get to do some factoring again, which I know you're so happy about. Okay, so example 2 says a vertical asymptote occurs at a given value that makes the function undefined. To find these values of x, we will take the bottom of each fraction and set it equal to 0. Solving for x will tell us at what point or points vertical asymptotes occur. Okay, so we're going to look at the bottom of each fraction. set it equal to 0, and solve for x. Okay, so the first one says f of x equals 1 divided by 2 times x plus 1. Okay, so we're asking ourselves here really, is there some number that would make the bottom of that fraction equal to 0? So to do that, we're going to take the bottom of the fraction, 2 times x plus 1, and set it equal to 0. And we're going to solve for x. So if you want, we can distribute this 2 and make it 2x plus 2 equals 0. And then we can solve it for x. We have x equals -1. So we will have a vertical asymptote at x equals -1. Okay, so that's part A. All right, part B says the function is, so f of x equals x squared plus 1 divided by x squared minus 1. Okay, now you can do this one of two ways. I'm going to have us factor it because we've been practicing factoring a difference of 2 squares. Okay, so the bottom of this is a difference of 2 squares. And if you remember, the way you do that is we need to find the square root of both terms. So x and 1. And then the way you write the factors is like this. X minus 1, x plus 1. Now, we are not factoring the top because that is not a difference of 2 squares. That's a sum of 2 squares, and there is no way to factor that. So we just factor the bottom part, and we're going to set each factor now equal to 0 and solve for x. Okay, so we're going to have x equals 1 and x equals -1. So this problem would have 2 vertical asymptotes, one at x equals -1 and one at x equals 1. Okay, so there are 2 vertical asymptotes to that problem. All right, next up on example 3, we are still going to factor the function, but I also provided a picture for you. So example 3 says a rational function with common factors. Determine all vertical asymptotes of the graph f of x equals x squared plus 2x minus 8 divided by x squared minus 4. Okay, so we're going to do it. Now, if you notice that you can factor the top, you should probably do that. So if you notice this problem here, it's a trinomial on the top, and we've spent a lot of time factoring trinomials. So we're going to factor the top, and we're going to factor the bottom. Now again, I said we only really care about the bottom part being set equal to 0 and solving. But there's something special about this problem, so we want to factor both the top and the bottom if you can. Okay, so on the top, we're thinking about what we could multiply to get -8. That would add up to be 2. So that would be x plus 4 and x minus 2. Okay, and then on the bottom, this is a difference of 2 squares. So the square root of x squared is x, and the square root of 4 is 2. So it's going to look like this. Plus 2, x minus 2. Okay, now this should look a lot like when we were finding limits, and we had to factor before we could find limits. Because now you can cancel some things out. You can cancel out the x minus 2. So this, when you cancel out the x minus 2, this is now called removable discontinuity. And write that down. It's now called removable discontinuity. There's not enough space there to write it. Removable discontinuity. What that means is the graph has a hole there, but because we can factor and eliminate the common factors, it is removed and it does not create the vertical asymptote there. So since it's removed, it's not going to create a vertical asymptote there, but I still have x plus 2 on the bottom. So now I'm going to set x plus 2 equal to 0, and we're going to solve it. Okay? So the part that's left over here, the x plus 2, it's set equal to 0, and we have an asymptote at x equals -2. Okay? And you can see that from this graph that I drew you, because the curvy parts are the function itself, and that vertical dotted line represents the asymptote that the graph approaches but never touches. And as you can see, it is in fact at x equals -2. Okay, so that's example 3. All right. On example 4, we're going to find some limits from a picture. Okay, so I'm going to go back to the graph. All right, so example 4 says find each limit, and first of all, I'm going to draw the picture for you. Okay, so it looks like we have a vertical asymptote at x equals 1, and then our graph itself is going to come in like this. Okay, so now it says find the limit of this function as x approaches 1 from the left. Okay, so here's where x equals 1. Right here, x equals 1. We're coming in from the left, and it's going more and more positive, so that would be positive infinity. Okay, so again, as we come in from the left towards x equals 1, it's getting more and more positive, so that means the limit is positive infinity. Okay, now we're going to check the second part. Okay, so now we're checking out what is the limit as x approaches 1 from the right. This is the right side of the graph. And on the right side of the graph, it's going down, down, down. So that means the limit is negative infinity. Okay, so that's example 4. Now, there's a box here that says Theorem 1.15, Properties of Infinite Limits. So you can read that over if you like. Okay, we're going to turn the page and look at example 5. Okay, example 5 says determining limits. So because the limit of 1 as x approaches 0 is equal to 1, so I'm going to write this down. The limit of 1 as x approaches 0 is going to equal 1, and we discussed this before because there's no x here. It's just that number, 1. So the limit of that part's 1. And then because of this, the limit of 1 over x squared as x approaches 0. If we were to do direct substitution on this, we would get something like this. 1 over 0. And whenever you get 1 over 0, I know you're thinking that's undefined, which is true. But in this case, we would say that the limit is infinity. So from now on, when you have 1 divided by 0, the limit is either infinity or negative infinity. And in this case, it's positive infinity. Okay, so now, because I know the limit of these things separately, if I had the problem like this, and I was to find the limit as x approaches 0 of this, because I know the limit of that part's 1 and the limit of this part's infinity, I can add those together, and 1 plus infinity is infinity. Yep. So that's how that would work if you had something like that. You would find the limit of each part separately, and then you would add them together. So that's how that's going to work. Okay, so now we're going to do some practice problems to practice finding vertical asymptotes algebraically. And then your homework will have some things that you'll have to factor, as well as some things that you'll have to look at the graph to find the limit. Okay, so. Alright, here we go with the practice problems. It says, find the vertical asymptotes, if any, of the graph of the function. Okay. So, we're going to factor the bottom part of this, and then set each factor of it equal to 0. Okay, so I factored it, and now it says x squared over x minus 2, x plus 2. And since I can't cancel anything out, we're going to set each part of it equal to 0. So each part of the bottom gets set equal to 0, and we're going to solve for x. Okay, so we would have two vertical asymptotes, one at x equals 2 and one at x equals negative 2. Okay, so that's the first practice problem. Okay, the next one looks like this. Okay, so like I mentioned earlier, you cannot factor x squared plus 1. So we're going to attempt to set it equal to 0 and solve for x. Okay, so if I solve this for x, watch what happens. I have x squared equals negative 1. Can you square any number and have it equal negative 1? Well, not any real number. So, because of that, we're going to say there are no vertical asymptotes. And what this means is there is no value of x that will make the bottom of that equal to 0. So there are no vertical asymptotes. So if you try to set the bottom of this equal to 0, and you get something like x squared equals negative 1, which cannot happen, you say no vertical asymptotes. Alright. Okay, next one. We've got f of x equals x squared minus 2 over x squared minus x minus 2. Okay, the top part of this is not a difference of two squares, because the square root of 2 is not a nice whole number. It's not a perfect square. It's an irrational number. So we can't factor the top, but we can factor the bottom. Okay, so what could you multiply to get negative 2? That would add up to negative 1. Well, that's x minus 2, x plus 1. Okay. So now we're going to take each part of the bottom here and set it equal to 0, because I cannot cancel out anything here. Okay, and we're going to solve both of those for x. Alright, so we'll have two vertical asymptotes, one at x equals 2 and one at x equals -1. Okay, so hopefully so far that's making sense, how to factor it, and then you set each factor on the bottom equal to 0 if you can't cancel anything out, and then after you solve it, those are your vertical asymptotes. Okay, so we've got one more practice problem, and then you can work on your homework. So the very last one, 25, says x equals x squared minus 6x minus 7 divided by x plus 1. Okay, so we're going to factor the top part of this. What could I multiply to get -7? That would add up to -6. -7 times 1 is -7. It adds up to -6. Okay, and on the bottom, we have x plus 1. So as you can see, we can cancel out the x plus 1s. And if you remember, when you cancel something out, if everything's gone, a 1 replaces it. So what I'm left with now is x minus 7 over 1. Now, I cannot set 1 equal to 0 and solve for x because there is no x there. So, because of that, we're going to say that there are no vertical asymptotes because I cannot set 1 equal to 0 and solve for x. Okay, so there are no vertical asymptotes. Okay, so part of your homework will be like this, factoring and setting the bottom parts equal to 0 to solve for x. Some of your homework will be like example 4, looking at a graph to find the limit. Okay, looking at the graph to find a limit. It'll either be infinity or negative infinity. Okay, so that's what the lesson is about. I hope that made sense, and if not, you can email me any questions you might have. I hope that your day goes well, and I'll see you next time. Bye.